This session is for Math 31. We're doing a few other derivative type questions that have come up. The first one being first principles. So first principles is when we go back to the idea of taking the slope of a secant and then making the secant line shorter and shorter until it's a tangent line. So taking the limit as it goes to 0 of the secant line makes it a tangent line, which helps us find the expression for the derivative. It's certainly lots more work than just using the power rule, but think of it as akin to back in 30-1, where you would have learned how to do long division for polynomials, and then you were introduced to synthetic division, which was way easier. Still got you to the same answer, but one was sort of the longer, kind of more technical way, shall we say, and then the other one was kind of a shortened up version. So I have a question here that we're going to do, and it says this: find dy dx for y equals 2x plus 1 or x, and then it says using first principles. So just be cautious if you're doing a question. If it says this, using first principles, I'll make that a little bit more readable. Sorry about that. If it says that, then we can't just use the power rule. Now, it's great to know what the answer is, right? It's kind of an ace in our pocket. We can go and kind of have on the side, oh, I know what the answer is going to be from the power rule. But then we have to develop the answer from first principles. So I'll show you how that goes. So, here's a little hint. Let's go over and do the answer so we kind of know what we're trying to shoot for. We just use the power rule, which is kind of the regular way of doing things. So y prime is 2, because the derivative of 2x is 2. And then we get minus 1 x to the minus 2, or you could have. That's what we're shooting for as an answer. So we can kind of have that as our minutia of doing one of these questions, and you tell me, well, I'm stuck in the minutia of the question, but I know the answer is this. That is worth some credit. We'd have to look at exactly what your solution was in terms of how much credit was worth, but it is worth something. Okay, so how do we go about doing these? We identify that, and I'm going to actually change this to say f at x, because you'll more often than not see it written as f at x. We're talking about the point x, y, or the point x and f at x, more aptly. And then we're adding a little squinch to the x. So we call it x plus h, the h being a little squinch. And then we're looking at the next point, f of x plus h. So don't really want the x and the y particularly. We'll just look at it with the x and the f at x and the x plus h and the f at x plus h. The idea of first principles is find the slope of the secant and then find the limit as h goes to 0 as h gets very, very small. So what we have to do here is we have to kind of get set up to have our coordinates ready, and then we use the slope formula. So what we have to do is just rewrite this point as x comma 2x plus 1 over x as our f at x, or our y coordinate. And then here we take and rewrite x plus h, and then every place we see x, we put x plus h. So it becomes 2 bracket x plus h bracket plus 1 over x plus h. This is in brackets, and then that is in full brackets. Okay, so basically what we've got is we've got our x1, our y1, our x2, and our y2. So we set up to roll. We're going to find the limit as h goes to 0 of f of x plus h, take away f at x over x plus h minus x. So have a look at that. That's the second coordinate. Take the second y coordinate, take away the first y coordinate, divided by the second x coordinate, take away the first x coordinate. Now we substitute those different expressions in to get the x's in here. So we get 2 bracket x plus h plus 1 over xh, put that in bracket, minus, careful of the overall bracket, 2x plus 1 over x. The denominator, thankfully, is not going to be hard. Okay, we're going to get some things canceling there. All right, next step. So we got to do some algebra here. Do some expanding of the brackets. 2x plus 2h, getting the 2 to go through the brackets. Can't really do much with 1 over x plus h, so let's just leave it sitting there for now. Distribute the negative through the bracket, minus 2x minus 1 over x, and then all over the x's have canceled down here, we get h. So thankfully, at least the bottom's looking a little bit useful. Okay, we do have some canceling that happens, this 2x and this 2x. All right, now what we have in the numerator is we have 3 expressions, and we have to find a common denominator. So we have to dig back in our memory about how to do rational expressions, which would have come up not much in 30-1, more in 20-1. So we're making a common denominator. The common denominator on top of the terms is x plus times x, sorry, not times h. Sorry about that. Got a little boo-boo here. I'll fix that. Okay, so sorry. Sometimes as I'm writing away. So our common denominator is our denominators. One denominator, I'll just highlight it, x plus h. The other denominator, x. Okay, now we have to find the new numerators. So our original term here is 2x. And we don't have any denominator there. So it's going to have to be multiplied and then all over the h that's just sort of hanging around the bottom. All right, now work. So we got to get rid of all these brackets. Now see if you can follow along. I'm going to take the x and sort of think of it as out here. So it's 2hx times x. We're doing the distributive property. So we get 2hx squared plus 2h squared x. Have a look at that one. Pause the recording if you need to, just to double check your algebra. And then here, x. And then back here, I'll distribute the negative. So x minus h. Now, just to make sure you're okay with the denominator, I'll use a different color highlighter so you can see what I'm talking about. So these are a denominator, and this is a denominator. We can combine them all as one denominator. If you have any issues with that, certainly feel free to reach out and ask me, and I'll explain it further, but they're all denominators. So if we have a fraction divided by just a number, they all become the denominator in the bottom, okay? Now we have a little bit of canceling, not a whole bunch, but we can cancel this x and this x. And then we can go about factoring out an h from everything. So we take an h out, we get 2x squared plus 2hx minus 1 all over the denominator of x plus h times x times h. And that's great because look, we get to cancel these h's, and that's what we want. We want to be able to put 0 into h and not have a 0 come out in the bottom. So at this point, we're now set and ready to actually apply the limit as h goes to 0 by putting 0 into the h's. So I usually indicate this with an arrow. This is now going to be 0, and this is now going to be 0. Those are the only places we have h's left. So we drop the limit as h goes to 0 because we put it in, and we get 2x squared. The next term becomes 0 minus 1 over the bottom, which is x squared. So again, have a look. Lots of things happened there and canceled. Now, if we rewrite that, then we can divide the x squared into that term and the x squared into that term, and we get 2 minus 1 over x squared. And that overall. Sneak peek, here we go, back to the beginning, 2 minus x squared, 1 over x squared, 2 minus 1 over x squared. Yay, history, or we're successful, we got the answer. Lots of work there. Do, go back, pause the recording, have a close look at how we do first principles. Now, a couple other little things that have come up in our discussions that I want to talk about. So again, you might want to pause. I'm going to ask you a question. I'm going to ask you actually 2 questions here and get you to think about it, and then I'll answer them. So here's question number 1. What are we finding when we find the first derivative? So in other words, when we're finding f prime x or dy dx, or y prime, those all mean the same things. What are we finding? I think you're probably going to know what that answer is. I'll cycle back in a second. Second question is, though, that's kind of part and parcel with this is, what we find the second derivative, or f double prime x, y double prime. How do we, I'll write it with those 2 ways. Those 2 ways are enough right now. Okay, what are we finding? So you probably remember when we first introduced derivatives, that derivatives were all about finding the slope of a curve at a point. So the answer to this is we're finding slope, specifically finding the slope of the curve at a point. So it's all about finding slope, basically, really, to boil it down there. Now, what are we finding about the second derivative? We're finding how fast the slope is changing, or maybe said a different way, is the change in the slope increasing or decreasing? Okay, so really it's the rate of change of the slope. Is it increasing in size? Is it decreasing in size? So it's the rate of change of the slope. So first derivative is the slope. Second derivative is the change in the slope. Now, there was a question on one of our review assignments. I'm going to do my best here to try to get the picture up here on our board and talk about that as our last little bit. I don't want this recording to be too long. So let's see how this imports for us. Yeah, pretty small, but I have the ability to move it over here and make it bigger. Okay, so this was from our review assignment. I think it's 15A, something like that. The instructions, I'll just go and grab it out and write it the same way. So the instructions were, sketch the graphs of the first and the second derivatives. Okay, so sketch the graphs of the first and second derivatives. So remember, f prime at x, the first derivative, is the slope. We'll just talk about that first. I won't put the second one. It's the slope at the point. So a way to look at this, I was thinking about the best way to kind of show you this, is we can look at where on the graph the slope is negative, where on the graph the slope is positive, and where on the graph the slope is 0. And I thought maybe I'd color code it. Thought this might be kind of a good way. So as we're coming down here and we're drawing tangent lines where I've got the green coming, this is a negative slope. It's a changing slope, but it's a negative slope all the way down to there, okay? So in terms of my color coding, this is a negative slope. Then we end up getting a 0 slope. right here, right when we're at the bottom, our tangent line would be horizontal. Okay, so this has a slope of 0. Then carrying on, and I'll just keep on changing my colors. I use yellow. This is a positive slope from here up to here. If you think about a line going that way, that's a positive slope. And we've got, again, another 0 here. So that's another, I use the same color. I don't need to color code anymore. And then we've got a negative slope. Okay, so what that means is when we have green, when we're trying to graph the first derivative, the green is negative. It's going to be below the x-axis. So the entire graph before approximately -1-ish is going to be negative. Where I have the orange, let's start there. Those are 0. So now this is approximately where there's an x-intercept on the graph of the first derivative. And this is approximately where the x-intercept is on the graph of the first derivative. Then this is how it's going to look. Where it's green, it's going to be below. So it's down here somewhere. Then between where we have yellow, it's above because it's positive. So we would be able to kind of, we don't exactly know how high up it would go like this. And then on the other side, it's negative again. Okay, so where it's green, it's below the x-axis because it's negative. Where we are orange, we're on the x-axis because it's 0. And where it's yellow, it's above the x-axis. Something else that is super, super helpful, got to go back to polynomials, but really helpful. This is basically a 3rd degree polynomial. Remember, we know that because it has 3 x-intercepts, okay? It changes direction twice. So the first derivative has to be a 2nd degree, which is a parabola. So keep that in mind. And that's the problem we have. Okay, so the derivative is approximately like this nice little parabola. Now, how do we do the second derivative? The second derivative is the change in slope, whether it's increasing or decreasing. Okay, so that's what we're going to use for words here, increasing or decreasing. Okay, so let me show you how this works. I'll try to pick a different color for us here. So maybe this nice purpley color. Okay, so let's say I just put a little tangent line down here where you can see the purple. And we get, you know, we estimate the slope of that line. That's a pretty large positive number. So we're just going to estimate that maybe the graph, the slope down here is say -4. Okay. And then if we draw another tangent line right here, the slope is -2. It's like it's a little flatter, right? It's getting a little flatter, maybe -1. Oh, then it gets to a slope of 0. And then here we get to a positive slope of say 1, and then it starts to get steeper, a slope of 2 and a slope of 3. When we're graphing the second derivative, we're looking for whether the slope is increasing or decreasing. So let me write these numbers. It goes from -2 to -1 to 0 to 1 to 2 to 3. Those numbers are increasing as we go from side to side, right? From -4 to 3. So we've got, oh, sorry, I've got my numbers backwards. Oh my goodness, I guess we got to start again. I got my negatives in the wrong spot. This is a +4, +2, +1. And that's negative. Sorry, got that mixed up. Positive this way, negative this way. Maybe I better just start again. Sorry about that. Sometimes when you're trying to make these recordings, you get a bit messed up and trying to change all these things. So let me just go back to the beginning of my colors, and we'll just quickly kind of redo this just so we're clear. I'm sure you guys are sitting there going, oh, she's got that wrong. Okay, so down here where I'm darkening in, it's a positive slope. I had said about a +4 slope. I'm just guessing. I'm just trying to show you what's happening in the pattern. This was say a +2 slope. It's getting not as steep. This is a +1 slope. Again, it's not as steep. Then we got the 0 at the top. And now we're going into the minuses on this side, -1. It's getting steeper, -2, -4. Remember, these are just arbitrary numbers. I was trying to show you the change in the slope, and I made that mistake with that sign, sorry. So let's write these down. So we got 4, and then 2, and then 1, and then 0, then -1, then -2, and then a -4. So as we go this way, our slope is decreasing. So that means that we want to draw a line with a negative slope. Decrease means negative. Okay, so we're going to draw a line with a negative slope, and edge will come down here like this, and then our second derivative will look, as long as it's got a negative slope, something like this. Okay, so that's our second derivative there. Okay, so apologize for the putting the signs wrong on the slopes of the tangents, but hopefully that gives you a little bit of an idea of the few questions that we covered.